please put your hands together for Robert and Daryl.
Oh, what an introduction. Amazing. Kia ora and g'day. So this is a bit like a game of rugby. It's going to be in two halves, so I'm going to present at you for 15 minutes, and when you're bored with me, I'm going to hand over to Robert. I'm going to talk a lot about theory, and hopefully he's going to talk more about practice, so if you don't like theory, hang in for his section. We may have some time at the end for some questions. I can ask him questions. That might be so exciting. It'd be a lot more interesting if you could ask some questions. So think of some while we're boring you to tears for the next 30 minutes. If we could get to my first slide, which is not that. Okay. So I do contract work at the moment for an organisation called Building 4.0, which is a Commonwealth government-funded research centre trying to advance the state of the construction industry. And we have a current project working with Homes New South Wales, which is a social housing agency in Australia, and they're probably the direct equivalent, really, of Kāinga Ora. And they gave us a little challenge about a year ago when we started this, and in my words, not their words, always dangerous putting words in the mouth of government, really, the challenge was, can we increase supply without compromising design quality or build quality? Can we use resources more efficiently, and can we speed the whole process up a lot? So a pretty simple statement, easy to sort of address, and a pretty common statement for a lot of government agencies around the world at the moment. Why are they asking that? Well, they have a backlog of some 50,000 families with nowhere to sleep tonight, so they're very interested in how do we deal with that problem. They have a large portfolio, about 130,000 properties, and they have a decent budget. They have about $5.2 billion to spend on doing something about this problem. The question they've asked of the research is, what is the role of MMC? Is it a silver bullet, or is it more of a silver axe that just can't chop wood? And I think before we dive into the MMC question and then the digital question in relation to that, we really have to come back to, well, why do we need to do anything different? We have this construction industry, so what's the problem? Why can't it scale up and build all these homes? And helpfully last month, the Australian Productivity Commission released this paper, and the news is all bad, and it's getting worse, and it's a long-term problem. And so if we look at the curves there, and I apologise, this will be the only graph that you'll see in this presentation, and it's been written by economists, so, you know, bear with me. The top curve on the graph is the Australian general curve of industry productivity. And it's a great story because over 30 years, they've improved their productivity by some 50%. The residential construction sector has gotten worse by 12% in the same time period, which gives you a 60% gap between all other industries and residential construction. Now, before you get too cocky and think, there's another thing Aussie sucks at, not just rugby union, right? The data is the same in the UK, the US, Germany, and New Zealand. So we have a global problem here in terms of worsening productivity. So now we come to the MMC question, and I think it's worth looking at it across a continuum as to how MMC is actually applied. And by MMC, we're using that as a sort of catch-all for prefab and modular and all those kind of technologies that we've talked about for decades. And at the left-hand end, in the most sort of traditional approach, what we see is design teams produce a fairly conventional design response. It's completely custom for a particular site. And at some point in the process, a contractor usually says, why don't we apply some MMC to this? We used bathroom pods in my last job. I'd like to use them again. They worked well. And that happens. And the building gets built, and it's a technical success. But commercially, nothing's achieved, right? There's no cost saving, there's no time saving. We get to the end of the project and go, well, what was all that about? It really didn't achieve much. And so the next attempt is usually to move up the curve a little bit and say, well, what you have to do is have some early contractor involvement. And so now we're still doing a completely custom design for any given site. It's still a largely conventional design process. But what we're doing is we're feeding in some of these experts from an MMC supply chain, and they're sitting at the design table while this is taking place. And through their inputs, we actually get a better commercial outcome. We see projects now starting to deliver commercial savings, time savings, quality benefits. But they're not game changers, right? They're sort of more in the order of 2 to 5% outcomes. And that's useful. We're always looking for those kind of savings. But if we go back to thinking about that productivity curve, it's barely going to arrest the fall. It's not going to take it back on a climb to meet the rest of the Australian industry. So with the research, we've looked at this and we've thought about it and said, well, really, this is not actually a construction problem at all. This is a design problem, because design is the input that construction is responding to. So if we really want to do something different in the construction space, we have to do something different in the design space. And where we're advocating is to look at a system-based approach using standardised components, very similar to some of the work that Jennifer was just describing. And if you take one thing away from the slide, or indeed this whole presentation, it's really the statement at the bottom. I think for too long MMC has been really about, can we take all the work off-site? Let's move it from point A to point B, and somehow magically it'll be a whole lot better. And that doesn't seem to unlock much value. But if we can instead translate buildings into products that are repeatable, that unlocks the awesome power of manufacturing. And so that's what we've been advocating in the research. So that looks like a standardised system, but it's got a couple of features to it. It has to have some very clear rules and principles that guide how the whole thing works. They have to drive compatibility and standardisation between all these components. But very importantly, we believe this should be an open and curated system, open for anybody to use it, not just a government agency, but any government agency, any private sector customer, anyone in the world who wants to pick up this system and apply it. And we believe that because the more people using these kind of systems, the more scale they have, the more maturity they have, the better the economic impact of them. They do need to be curated. We couldn't imagine a system that was without any curation, that it would probably lead to a fairly chaotic series of outcomes pretty quickly. And we believe in interchangeable components. And so, as you heard, I've done a lot of work in mass timber. I love mass timber. But if we don't want to build in mass timber and we want a different material, we should be able to put that material in or switch it out to another material and it all be compatible within the same system. It should be somewhat independent of those material choices which are project specific. We have talked about using 2D components as opposed to large format volumetric assemblies, and the reason we do that is really this slide, where we're trying to balance the idea of design flexibility with part repeatability, and it's a bit of an art, I guess, to find where these parts should be and what we should focus on. But ultimately what we get to are these items down the bottom here, which are still relatively small. They've come up above the atomic level, the nuts and bolts, and we come up above that level because that was all standardised about 150 years ago, so we don't need to do any work at that level. But we're not recommending going much further up than that. And we tend to think about this as a mix of ingredients at the bottom that we want to standardise, more so than the recipes you might apply them to. And the big kind of economic theory that sits behind all of this is Wright's law. And Wright's law, which I've talked about publicly a number of times before, is a really straightforward statement that says every time industry doubles a batch size, it tends to produce cost savings of about 20%. It also tends to generate big quality improvements. So it's not a race to the bottom. As we double these batch sizes, we find quality uplift and cost decreasing. And there's no magic in that. It's pretty straightforward, right? It's this top line principle here that when you do something over and over again, you have learning effects. If I ask you to do something once, you've learnt something from the process, but you have nothing to apply that learning to, which sounds like most construction projects. If I ask you to do it 10,000 times, you'll be amazingly intelligent about how to do it. You'll find all kinds of shortcuts and efficiencies, and the industry will be able to produce things much cheaper. To get to that learning effect, you have to have this consistency of solutions, hence the importance of some standardisation. But we also believe you need things like a distributed supply chain, so you're not trying to put this all under one roof or one business. And then really the fourth point, if you've designed these standardised components, then you have a challenge. And I've talked about this before, architects in the room, that getting architects to use standardised components can be a little bit like training a cat to be a vegetarian. It doesn't always end well for both parties, right? But it is really where we need to start focusing if we're going to get outcomes from this kind of approach. I won't go through all the system principles in the interest of time, save it to say there are some very important principles that drive the thinking. For example, when we talk about part standardisation, it's important not to go to 100%. We believe you're looking for about an 80% standardisation, and if you try to go to 100%, you really defeat what you're trying to obtain in terms of design quality. So the kind of Pareto principle that needs to apply there. What does a system look like? Because we talk about these things all the time. Well, the most sort of traditional, simple understanding of it would be that ring binder we heard about earlier that sat on the shelf that you could leaf through and say, here's the rules, here's the principles, oh, here's a list of the components. but you can see where this can start to begin a digital journey for what we might do next. And what's important here is that these principles drive into requirements which are then given to industry for them to produce a response. Because we don't believe it's necessarily a job for building designers to figure out how to manufacture products. And so you want to bring the supply chain into the process and have them react to these requirements so that they can then give you back these standardized components you can bank into your library. To get the process started, for the last 12 months, we've been developing conceptually a list of parts. I won't go through them. If you're interested in this work, I'm going to share a website link at the end where you can drill into more detail about it. But these are the beginning points. These are not the ends. This is the thing that goes with the requirements to supply chain to say, hey, we have this idea for this thing. How do you make it real? How do you bring your understanding, your technologies, your methods and apply it and turn this into a really valuable part that we can utilize over and again? We have some ideas in the way that it comes together which we think are useful. Again, not going through all of these, but to pick on the second one, decoupling the wall finishes, we said, well, it might be interesting if we can make the finish independent of the structural element of the wall. We actually used a great New Zealand product there, a company called Fastmount, that has a series of clips which will allow you to attach finishes to frames. And by doing so, we get an architectural diversity of finish, and we free the wall up to be a very standard element in behind it. We did other things like we concentrated where the services sat. So we've come up with these modules which go outside the building on the balcony. It's not the first time this idea has been applied, but we're trying to do it at scale. And so by putting all the services together into this engine bay, essentially, we've got a thing that's easy to manufacture, it's easy to install, and for a fleet owner like Homes New South Wales, who will own this property for at least 100 years, it's very easy to maintain. They don't need to go through someone's home to get to this thing, to pull it apart and replace the air conditioning or the hot water service or the fibre optic or all the other things that are located in there. That connects back into the building through a horizontal assembly, and it gets to a smart wall that sits between the kitchen and the bathroom to bring those services into the dwelling. And by doing all this sort of thing, we've really thought about how a service is distributed, how many fire penetrations do we need through the building, how accessible for maintenance is it all, can we upgrade it in the future. We've done similar things with the facade, where we've broken that down into multiple layers. And we've done some really simple, obvious things, which I wonder why we don't do more often. So we've said, let's just have standard window sizes. We don't want any more site measuring of windows on site, right? So if we have enough range in this catalogue, there is no reason to have a randomly sized window going forward. Similarly in the balcony, we've produced that as a kit of parts, and of course there is a wonderful company here today showing a similar kind of concept. And what we're doing right at the moment is trying to culminate this in a display apartment that will be finished in July, all things willing. And if you're in Sydney in July, please hit me up and I'd love to give you a tour of that. And so that's all about physical parts and a system of engineering really to bring those things together. What is the digital opportunity? Well, we're at the end of stage 1 of this research, and we're about to embark on stage 2. And really one of the most important things I think we have to do in stage 2 is start laying this digital foundation for this. And the question that Jennifer got before was, well, how do we scale digital? And I kind of think about it the other way around. We have this physical system where we want to build a lot of homes, we want to do them well, and we want to do them fairly rapidly. We're trying to scale that. And digital is the answer to how we scale that, rather than let's focus on scaling digital. So the obvious applications, and this is my last slide, and you'll be relieved to know, is we really need this idea of system integrity. So how do we herd these cats that want to constantly break the rules or ignore the rules or won't read the rules in the first place? Well, it'd be kind of nice if the software sort of curated that process and kept them on guide rails and didn't let them break the rules. We're also looking at the idea of software that provides real user support, right? It'd be nice if the software did things that we couldn't do otherwise. So, for example, can I get a real understanding of costs as I'm assembling the design? Not after it's finished and it's been sent off to some cost estimator and I get a number back 3 weeks later. So software exists today that will do that. And we're in, I guess, an analysis mode of looking for how we can bring all those pieces together. And then most importantly, if we're talking about a system of distributed parts from many manufacturers, there is a lot of threading to do to bring this patchwork quilt together. And is that a digital twin? Is it some other tool? but we definitely need to find a way of creating that digital thread to make the assembly of the parts. But the last point is one we often overlook, and I want to emphasise it. Our industry is really short on benchmarking and analysis on how we're going and what we're doing and what users feel about our products and how we can improve them. And I don't want to wait 30 years for the next Productivity Commission report to find out we haven't been doing a good job. So with that, I'll hand over to Robert and we'll hear about the practical.
Thanks, Daryl. I'm just going to set this up very quickly. It's going to be hard to follow Jennifer and Daryl this morning, but I'll do my best. Thanks, Petra, for the introduction. That should, comes up. Okay, so super impressed. Daryl was perfectly finished on time. So, Armour. So we started Armour about 2011, so almost 15 years ago now. So background's really in complex, computationally driven design and fabrication. And so today we're applying that expertise to create scalable solutions that align with Daryl's push. So a really big fan of Daryl's thinking and how we can use some of the expertise over the past to then develop some increased productivity, quality and speed. I'll let this play through for about a minute or two. This shows some of the work that we've done in the past. So where Daryl's outlined how modern methods of construction and component-based systems can revolutionise productivity, I think what I want to show you is through our work, it's often high-end and bespoke, uses the same fundamental principles to manage complexity and create repeatable, adaptable solutions. So really, there's a few projects here, and I'll come back to them later, and we'll have a look at some of the principles. But this is 580 George Street. Generally, everything we do is modelled comprehensively on the computer. So we'll model every single part and component. It'll go into bill of materials. It'll be labelled, named, and accounted for, and it'll be costed. And we always start with the model. The model produces the drawings. The drawings are an artefact and output of the model. We'll always 3D scan the entire building as we're working. So we're working with real as-built information rather than as-designed speculative information. Everything we'll do, we try to bundle. So we use techniques of bundling and unbundling. So we try to take all the complexity out of the system. And you'll hear about systems and interfaces a lot, I think, this morning. But take all the complexity out of the system and bundle into into one complex part that we can handle and manage effectively rather than have it dispersed. Here you can see this is Grosvenor Place, Harry Seidler building, a mirror polished stainless facade panel, and the system designed for that, and Wynyard Walk, which I'll talk about a little bit later as well. So Wynyard Walk, some infrastructure in Sydney that connects Wynyard down to Barangaroo. Again, some of the techniques will be, in this case we're using CATIA, which is an aerospace and automotive package, but again this is really to handle the level of complexity and the amount of parts effectively in a computational way. We'll couple all of this, whatever we're doing, we'll write small bits of software, scripts and programs to help us automate both the modelling and the documentation. And we're doing that more and more to the point now where we're actually building plugins and writing our own software, such an extension to FrameCAD and light gauge steel manufacturing to help really connect the design through to manufacturing. And that is really what started Armour to begin with. It's a hyphenated practice, architectural research and then material applications. And the whole idea is really to bridge that divide between design and production through computation. So what I want to do now is just dive into 4 projects quickly and pull out some principles that illustrate this concept. So number 1, 580 George Street. And the principle here is really to concentrate the complexity. So again, we've got a parametric model as a single source of truth. I think this is common now, but it wasn't at the time. And this is this bundling strategy. So we've taken all of the complexity within the system and we've built it into one bracket which has the same detail. And there was about 6 months worth of work just in designing this bracket with Arup and the contractor. And that bracket can then, you can see this cruciform bracket on the plywood. And this bracket it's exactly the same bracket. It's extruded, custom extrusion that we bring in from China, and then plywood backing, which allows it to move in and out, which then allows us to deliver the facade. And then we couple that with 3D scanning and just-in-time fabrication. So as soon as the structural steel goes up, we scan it, and then we output fabrication for the plywood. Brackets are all there. Bring it to site and put it together. And what it allows for is in thousands of unique components, which is simplified, which allow us to really, I guess, hit those targets. Second principle is variability within constraints. So how do you achieve a bespoke finish and variability, but still maintain constraints such as cost and time? And so with Wynyard Walk, we used a parametric product template, again, built in CATIA. So a very sophisticated template which allows it to adjust parametrically to different site conditions while still maintaining a very rigorous set of and small set of details and a repeatable fabrication logic. So this allows a degree of variety within a standardized system of components. And how that relates to housing is it allows us to achieve site-specific solutions without reinventing the wheel or blowing out costs, which I'll show you in a minute. Third principle is Darling Exchange. Within Darling Exchange is this idea of fixed, flexible, and free components, which Daryl spoke about earlier. So here we've got fixed substructure being the steel brackets, and then flexible cladding configuration. So everything is modularized and prefabricated off-site, delivered to site, and then installed. And then with free bespoke elements on the front. So the whole thing ties together. You wouldn't know that it's actually a component-based system. But here you can see how one of those panels is lifted off straight off the truck and then onto a crane and straight onto the building. So this is for Lendlease, working with Kengo Kuma and Arup. So almost agricultural detailing, super simple, but very effective in its end result, I think. I'll jump forward. And then again, to echo Jennifer's talk earlier, this idea of system of systems. So how you have multiple systems come together and the holistic effect they have. So in this one, this principle's extracted from Trifolium, an earlier project of ours, design project. So here it's really about designing clear interfaces between your different systems, and then the co-relationship that each system has on each other and how we can use that to reduce duplication. So here we've got a Corian structure held together with steel, which then bridges off to hold internal steel lining. This was over the top, every single thousands of parts and components, every single one is unique in this case. However, they all do share the same connection detail. So to sum up these lessons, number one, system of systems design. So clearly define those interfaces and subsystems and then integrate them so that each part's doing double duty. I think that's one that's easy to achieve. The second is having those variability within constraints. So use flexible product templates, and we can do that through software, and parametric models, and keep the details tight and less in number. So no ad hoc detailing. Everything should be based on the system. Third is this idea of fixed, flexible, and free. So just like car manufacturing, aerospace, Jennifer and the experience with Airbus, we also visited Airbus in Toulouse, so super useful. standardize the unseen components, and then customize where it counts. So on the facade, on the areas that people touch. And then lastly, concentrate the complexity. So think about bundling and unbundling, and just like in product design, how you can apply that to architecture. So bundle those specialized details into one single complex part, which is variable through parametric design, and then can be automated in manufacturing through laser cutting, etc., to keep it simple. So we're taking all of that thinking, where does that land us today? And so what we're working on at the moment, still doing all the same work, but is using that experience with really high-end projects that have no budget to then bring that back into a solution for a problem that we're really at today, which is housing. So Fabrica is the culmination of this, and this is really thinking about using those principles to develop a housing product that uses prefabricated parts, which are such as panelized wall systems, volumetric bathroom pods, joinery pods, and then clip-on facade systems to deliver housing which is much, much faster, a little bit cheaper, and much higher quality, and also allows it to be bespoke. So all of this is variable, site-specific, and user-specific. So it's a systemized approach to housing based on those same principles. And sort of, when you look at from Trifolium to Wynyard's parametric templates, the principles highlight that well-defined, repeatable parts can deliver high-quality, efficient housing. And so really, I guess the thing that I'd ask you to walk away with is how do you manage complexity well, and how you manage it, how does that allow us to then standardize intelligently? And so within this, I think the real benefit is that as you start to move to a systems-based approach with a catalogue of parts, how those parts can be reused across different projects and different scales to achieve the results. So in this case, we've got fixed, flexible, and free components, or categories of components, such as bathroom pod, kitchen, window, door, and then reusing them on small-scale residential up to mid-rise, the same component across those scales. And because we're doing that, because we're reducing our SKU count, it allows us to spend much more time designing and engineering each of those parts, hopefully achieving Wright's law. So that's what I'll leave you with today. Thank you very much.